Hello, Dr. Rogers and Sam. This is my lecture on Chapter J, Polymers. Um, this chapter is all about polymers and their structure and their chemistry and their formation, really. So, the objective for after you finish this chapter are these bullet points under here. You'll see that as with metals, a polymer's properties are closely tied to its structure and its features. In this chapter, we will look at the molecular and crystal structures of polymers. By the end of this chapter, you will be able to understand the chemistry behind polymers, understand the structure and arrangement of polymers, and be able to analyze the formation of polymers and their crystal structure. All right, getting started here. For hydrocarbon molecules, hydrocarbons are hydrogen plus carbon, kind of intuitive. Covalent bonded molecules are present in hydrocarbons, where each of the two bonding atoms contribute only one electron, just like in the picture below. Molecules can have double and triple covalent bonds between the carbon atoms, like you see right here. That's a double bond there. These are unsaturated bonds. Weak hydrogen and van der Waals bonds exist between these molecules. And that's good to know for later when they start bonding with other things. Isomerism is a phenomenon where compounds with the same formula can have a different arrangement of atoms. A little example here, butane, C4H10. I think that's what it is. This can have two possible isomers. So the butane we all know, they're pretty simple, just four carbons like that, but it has an isomer that can also be drawn a different way, even though the formula looks the same. So that will look like this. As you can see, there are still four carbons, but it is drawn in a different way and will have a different name, even though the formula is the same. So this would be 2-methylpropane, but yeah. So those are isomers. Okay, polymer molecules. Big chains of hydrocarbons referred to as macromolecules. So these are essentially just long strands of hydrocarbons to form these macromolecules, which is what polymers are. Uh, the foundation, they're called monomers. They're the foundation of polymers. These are the small molecules that are repeated to form the long chains. Monomers are hydrocarbons. Common functional groups of hydrocarbons, you'll see down here in this little table from the textbook. Uh, Obviously, alcohols, where you have this OH at the end, that's what defines those. Ethers, oh, ethers, and that's when you have an oxygen in the middle of two carbons. You'll see acids, aldehydes, and aromatic carbons. We won't get too much into those uh, in this lecture. Chemistry of polymers. Polymer molecules will react and bond with these functional groups to have different properties and to make new products. Uh, these are denoted as our groups. Just a little name for them, because you see here are can just represent the carbon chains that these characteristic units are bonded to. And these new substituents, these R groups, turn the polymer into a whole new compound with new properties. Example. So an example of the formation of polyethylene. So let's take this hydrocarbon here. This is ethylene, okay? Simple hydrocarbon like we saw all the way up here, just the same thing. Very popular in the formation of polymers. Move it over there. So, under the appropriate conditions, we can react this to transform it into polyethylene, like one of the most popular polymers in the industry. So the process begins with like the R groups as we were talking with before of this ethylene monomer that I just drew. So if we draw this molecule here with this R group, continued chain pretty much. Um, this one will also have an R group. Oh, no, not an R group. That dot I just drew is a free electron, not bonded with anything. That'll just help with the reaction. Okay, so we have this for the setup. All right, so these two are going to come together. We can see that like it is here. Uh, so it's a sequential addition, as I said before, repeat units of these smaller monomers that I just drew, and that's what's going to turn into our long polyethylene chain. So let me draw it here. You're essentially going to get this guy right here coming over and attaching himself to this chain here. That's going to remove this double bond here, because now it's going to have one extra bond on it. So that bond is going to come off so it can connect to the chain. Kind of like this. All of these are going to have hydrogens because it wants carbon wants four bonds to be stable. And you see this one on the end. This one does not have four bonds. So what's going to happen with that? We saw that these both have R groups. I talked about this free electron earlier. Basically, when this comes to attach to this R group, the R group will attach from where it is, as you saw over here. So here's the cutoff. On this side, that's this molecule here. And on this side is the other one. So as it came on here, it basically just snapped into place. This bond attached here. So that's why there's no double bond over here. This free electron, however, it is just going to hop and hop and hop and hop all the way down this new polymer that we made, uh, all the way to the end to hang out with this guy. So now it is how it wants to be. It has that extra electron group because it's missing its fourth bond. So yeah, that's the formation of polyethylene, this group right here. Um, and pretty much it's just, it can go on forever. So we can write it as a more general chain actually. So if we move this over here, just the general form, it'll look like this. To the end. It'll just go on forever, like however you want, how long you want it to be. That's what it's gonna look like for you. So yeah, degree of polymerization is directly correlated with this. We can find this with a very simple equation. Looks a little like this. So we see Mn here is the number average molecular weight, pretty simple. And then M is the repeat unit molecular weight. So it's the repeat uh, molecular weight of the repeat unit, so the monomer. Uh, Mn, we can find that with another simple equation equals the sum of so really all this is just playing with the molecular weights of the species you're adding together and just taking the average of that. And then divide that by the repeat unit. So that's how you get your degree of polymerization. Pretty simple. Down here, we can see what we just made. So we already know there's a repeat unit that repeats just forever, or as long as you need it to. Uh, as we've drawn it, it's just a straight chain, like just for simpleness, really, when we're drawing it. In reality, it has this zigzag shape. This is just because of the interactions between the molecules. It wants this 109-degree bond just for stability. So that's how you'll actually encounter it in nature, but for simplicity, we'll draw it with straight lines for now. Molecular structure, linear. Linear structure, polymers are joined together end to end in single long chains, exactly like we just saw up here. Simple molecular structure. Branched side branches are connected to the main linear polymer chain. So imagine we just had a branch coming off here. That's what that would look like. Cross-linked adjacent linear chains joined together at various positions. Just another step up from branched. And then network, multifunctional monomers forming three or more active covalent bonds to make, oh, what was this? Yes, three-dimensional networks. Sorry about that. Yeah, so there's a bunch of different kinds of structures you can have, and foundationally, they all start with the linear. Stereoisomerism and geometrical isomerism. So this is a tricky just fact that is in the nature of these types of molecules. So like we saw before, just quickly, isomerism is when two or more compounds have the same formula but different structural energy or structural arrangement. We saw that with butane, and I gave a little example up here. But there's different kinds. We can go a little deeper into that. So stereoisomerism are atoms linked together with different spatial arrangement, uh, as we can see in the picture below. Uh, there's two types of configuration. Cis configuration has all the R groups on the same side of the chain, as we can see here. All these filled in, these wedge bonds are facing towards us. The dashes are facing behind us, just so you have that 3D shape like it actually is. And then the second kind is trans configuration. So all the R groups are on alternating sides as it goes down the chain. Uh, tu- tu- tu. So yeah, Oh, sorry, I seem to jumped ahead a little. These don't pop up yet. We have different names for these. So this would be isotactic configuration. Sorry. This would be syndiotactic configuration, and then atactic down here. Sorry about that. Has random positioning. So there's no real order to it. Uh, it's kind of just random across the chain. Now down here for geometrical isomerism, which I mistook before for stereoisomerism, carbon atoms linked by double bond have alkyl groups that can be situated on either side of the chain, just like up here, but there's double bonds involved now. So cis structure, like I said before, is when the substituents are on the same side. Trans is when the substituents are positioned on the opposite sides. So we got that cleared up. Down here, just a little schematic of polymer molecules. So you can see up here, just molecular characteristics, has all these things to take into account. We're really focusing on the structure here. So we saw these types of structure. Now isomeric states, we saw stereoisomers, we saw geometric isomers, cis and trans. And here's the definitions I just gave. Now getting into the crystallinity of polymers. Polymeric molecules can be in a crystalline state. The packing of molecular chains produces an ordered crystal array. Pretty interesting. And these crystal structures are specified in terms of unit cells, of course, just like metals we saw earlier in this class. These unit cells are very complicated. I'm not going to go too far into them. Not going to draw any. Here's an example right here. Look at this crystal structure. That's what polymers look like. Polymers are only partially crystalline, up to 95% at least. Therefore, the molecules will also be partially amorphous. So not totally crystalline. They're going to have a little bit of that like liquid property, which is what the amorphous is like. To calculate this pretty simple formula, percent crystallinity, we can find that. We know we can go up to 95, as I just said. Equals. So we have rho here for density. Yeah, it's pretty much just a density formula. There, times 100 for percent. There's the formula. And this is where, so PS is the density of the specimen, PA, density of the totally amorphous polymer, and then PC is the density of the crystalline polymer. So yeah, these values must be obtained through experimental means. So yeah, we're not going to figure out how to find them. We're just gonna do this example down here where they are given to us. So let's get started for this example. The computation of density and percent crystallinity of polyethylene, like we found before the formation of it. So let's try and compute the density here. The equivalent of two ethylene repeat units is contained within one each unit cell. It specifies that for us. So let's go back and remember this formula from earlier in the course when we were looking at unit cells of metals. So N here represents the number of repeat units within the unit cell, and we're not really focusing on moles here. and A is the molecular unit weight. So let's go ahead and specify A here. A equals 2AC plus 4AH. So, and if you weren't totally clear, we're getting these numbers because equivalent of two ethylene repeat units. So we know there's gonna be two carbons. How many hydrogens are gonna be in the carbons? Four, okay? Because just to match those bonds, like we already know that from the example we saw all the way up here. So let's just we'll give these atomic weights. We can just simplify this 12.01. Let's give units here, grams per mole, just the atomic weight of carbon, plus 4 times 1.01 grams mole. Atomic weight of hydrogen, pretty simple. This comes out to 28.05 grams per mole. So now we have A. Uh, so next step would be to find VC because we have N and A already. VC is the volume of the cell, just like when we were doing metals. Uh, if we go to a standard unit cell up here, like I showed the picture for, these measurements are just standardized. Oh, where did I lose it? We can see these measurements here. We're going to use those for our 1 unit cell of uh, the polyethylene. And this is going to be in nanometers, of course. Yeah, pretty simple. Just finding the volume. This comes out to 99.33 times 10 to the minus 23 centimeters cube per unit cell. All right. And now we're just plugging into the equation. So we can just do this 2 times 28.05 up top. Put units on that. And then on the bottom, we have the volume 9.33 times 10 to the minus 23 centimeters cube units. So times Avogadro's number 6.022 times 10 to the 23. Repeat units a mole. All right, pulling out our calculator. Good calculating, we get 0.98 grams centimeter cube. All right, and that will be our final answer. That's the density of the polyethylene. We can now move on to B. So using our answer obtained, calculate the percent crystallinity of a branch polyethylene, and it gives us the specified experimental values that we couldn't find ourselves. So let's go ahead and pull that formula down. Crystallinity. Okay, so we'll go back up. Calculate the percent crystallinity of a branch polyethylene that has density of 0.925. Um, Density of the totally amorphous material gives us that too, so Pa equals 0.870. And this is really just a matter of plugging um, the values in. So we found the one up there, we found these two. So yeah, that's what we're gonna do is we have PC, the crystallinity, the density there, polyethylene. We have Pa, 870, and we have PS, the value we just found here. Let's plug those in. 0.9 denominator. 0.925 grams centimeter cube. Now we'll get click back in on the calculator, find this answer. It should come out to be, oh, we can't forget the times 100 for percent. Should come out to be 46.4%. So yeah, that's just a small example of using some old facts we knew, this equation here from just our general knowledge of unit cells from the metal chapters we focused on, and then applying it to percent crystallinity of this new chapter here. So yeah, that's all about polymers and their structure and their chemistry. And yeah, I hope you enjoyed this class and lecture. That's polymers. Thank you.